we are going to see two examples of how the power method approximates the second smallest eigenvalue of the Laplacian of a graph. First, recall that the way the power method approximates the second largest eigenvalue of a given positive semi-definite matrix is simply to pick a random vector with plus minus 1 entries, then shift it so that it becomes orthogonal to a known eigenvector of the largest eigenvalue, and then multiply x by a sufficiently large power of the matrix M. Here, for k, it's sufficient to be 1 over epsilon times log n over epsilon, where epsilon is the additive error that we allow. When we want to compute the second smallest eigenvalue of L, approximately, along with a vector of approximately optimal Rayleigh quotient, then we're going to define matrix M, which is essentially minus the Laplacian, so that the eigenvectors of M and L are the same, and that they appear in sorted order in the opposite order, so that the second largest eigenvalue of M will give us the second smallest eigenvalue of the Laplacian. We cannot quite define M to be minus L because M needs to have all the eigenvalues to be greater than or equal to 0. And so we said that we're going to define M as 2i minus L, or for better numerical stability, the identity minus half of the Laplacian. The identity minus half of the Laplacian is the same as half of the identity plus 1 over 2d times the adjacency matrix. The computation then will be to pick a random x with plus minus 1 entries, then shift it so that it becomes orthogonal to a known eigenvector of the largest eigenvalue of M, which is the same as a known eigenvector of the smallest eigenvalue of the Laplacian, which is just the all one vector. So we shift x so that it becomes orthogonal to the all one vector. Basically, we shift x so that the entries of x will sum to 0 after the shift. Already for a vector x randomly picked with entries plus minus 1, the sum of the entries will be small, so this will be a small shift. And then we multiply x by m to the k, which means that for k times, we multiply x by the matrix M. A multiplication of x by the matrix M will be such that after the product, the vth entry of x will be half of what it was before, corresponding to half of the identity, plus 1 over 2d times the summation over the neighbors of v of the value xu. So the vector after one multiplication by m will be such that every entry is going to be the average of what it was before and the average of the neighbors of the corresponding vertex. So the entry for every vertex will become some kind of convex combination of what it was before and what are the values taken by the neighbors, starting by a properly shifted random plus 1 minus 1 vector. Now let's see how this algorithm performs in computing an approximate eigenvector for the second eigenvalue of the Laplacian of a cycle. So here we have a cycle with 31 vertices. In this drawing, the dots correspond to vertices, the lines are the edges, and the vertices are positioned so that their x coordinate is the same as the content of the x vector in the algorithm. The y coordinate is just assigned to make the drawing more readable. It will be the same at every iteration. Initially, the x vector is just random plus 1 minus 1 values, shifted in order for them to sum to 0. Then at each iteration, the value of every vertex is replaced by the average of what it was before and the average of the neighbors. So for example, this vertex will become half what it was before plus half the average of the neighbors. So we're going to see some vertices that were close to minus 1 be shifted to be around minus 0.5, and some vertices that were near 1 to be shifted to be near 0.5. Again, at the next iteration, every vertex will take the average of what it had before and the average of the neighbors. And see that every iteration, the arrangement is less and less random, and we start seeing the vertices that tend to want to be ordered according to the order in which they appear in the cycle. progressively the drawing will disentangle itself, because vertices that are far from its neighbors will tend to be pushed a little closer, and this will pull vertices that are close to be a little farther apart, and will also pull those high concentration of vertices away from each other. Remember that the Rayleigh quotient that we got will eventually tend to be very close to the optimal Rayleigh quotient, which means that the vector itself will be pretty close to being in the eigenspace of the smallest eigenvalue. But the error that we're going to have at every step will be roughly linear in the number of steps that we are taking. Now the second smallest eigenvalue of the Laplacian in a cycle with 31 vertices, it's very small. It's in the order of 1/1000. So it might take several iterations to perfectly get a vector that is essentially an eigenvector for the second smallest eigenvalue. But already after these 40 iterations or so, we see more or less the vertices being aligned in the way they would be by an actual eigenvector. But already if we give this vector as an input to the sweep algorithm, we will find an optimal cut of the cycle. Now here is the same algorithm applied to the hypercube, to a hypercube that has 16 vertices, so dimension 4. At the first step, every vertex is again assigned a random ±1 label, and then the labels are slightly shifted so that they sum to 0. And at every step, every vertex will be updated to be half what it was before, plus 1/8 the summation of the neighbors. This is what we get after one step. This is what we get after 2 steps. And already after 4 iterations, we're going to get pretty much the structure that we would see if we kept going for a long time. So the vertices are going to be ordered by this vector according to the number of zeros in their label. Meaning that if we order the vertices according to the corresponding entry in the vector, we're going to see them in the same order as the number of ones that they have in the hypercube. So this vector will be first in the order, and then so this vertex will be first in the order. These other 4 vertices will come more or less together. These other 6 vertices will come together. These other 4 vertices will come together, and this one will be the maximum. This is in fact a good eigenvector. It is in the eigenspace of the second smallest eigenvalue of the Laplacian. It's unfortunately not a good vector to use for the sweep algorithm, because it doesn't discover a optimal or a near optimal cut. But that's a known problem with the sweep algorithm when it's run using a random eigenvector from the eigenspace of the second smallest eigenvalue.